Batman, lowercase m is 80 kilograms, has spotted the Joker, uppercase M is 100 kilograms, lurking below on the floor of the museum. Batman swings down on a rope and collides with the Joker. After the collision, the two of them slide across the floor together and come to a stop. Well, this problem contained a hint in the wording in that it observes that there is a collision. Whenever we have a collision, we know that we will certainly conserve momentum, and therefore we will be placing moments just before and just after the collision. However, since the starting point of Batman is not just before the collision, we will put just before the collision as moment 2, and just after the collision as moment 3. Finishing out the moments in this problem, the initial moment before Batman swings down will be moment 1, and after the two of them have slid across the floor and come to a stop will be moment 4. We recognize that the collision between moment 2 and 3 does not conserve energy. It is a totally inelastic collision because after the collision, Batman and the Joker stay together. They don't separate. Also, we recognize that moment 1 to 2 will be conservation of energy, and 3 to 4 will have work due to a non-conservative force, where that non-conservative force is friction. We'll solve this problem by following the moments in time order. We connect moment 1 to moment 2 using energy principles, and since we notice that there is no work due to a non-conservative force, we solve this by conservation of energy, by setting the total energy at moment 1 equal to the total energy at moment 2. In order to realize this as an actual equation, we need to ask ourselves 3 questions at moment 1 and the same 3 questions at moment 2. At moment 1, do we have kinetic energy? The answer is no, because Batman is stationary. At moment 1, do we have gravitational potential energy? It depends. Gravitational potential energy is mgh, or as I prefer, mgy, and we need to define for ourselves what we will call y equals 0. It's traditional, or simplest, to define y equals 0 at the lowest point of the motion of the problem, and since that point will be moment 2, we will say that indeed Batman does have a potential energy at moment 1, and that potential energy will be m, for Batman that's 80, times g, times the height at moment 1, which is 3 meters. There are no springs in the problem, and so there's no spring potential energy. At moment 2, which is just before Batman collides with the Joker, we see that there is kinetic energy, and it is simply due to the motion of Batman. So that will be 1/2 m, his mass is 80, times the velocity at moment 2 squared. Since moment 2 is the height equals 0 moment, there will be no gravitational potential energy, and there are still no springs. Following the convenient cancellation of the mass of 80 kilograms, we find that the velocity v2 can be expressed as the square root of 2g3, which is 7.67 meter per second. We'll connect moment 2 to moment 3 using the principle of conservation of momentum. With momentum, we must always be careful because momentum is a vector and must be conserved in each relevant coordinate. However, since Batman is moving horizontally prior to the collision, and Batman and Joker as a pair are moving horizontally afterwards, this is indeed only a one-dimensional momentum problem. Thus, we realize our conservation of momentum equation by setting the momentum of the system at moment 2 equal to the momentum of the system at moment 3. We fulfill this equation by asking object by object whether they have a momentum at the appropriate moment. At moment 2, Batman, lowercase m, certainly has a momentum, but the Joker does not. At moment 3, Batman and the Joker move as a single object, and they certainly do have a momentum. Filling in what we know yields the following. 80 times 7.67 is 180 times V3, so the capital V3 is equal to 3.41 meters per second. Finally, we'll be connecting moment 3 to moment 4 using energy methods. However, because of the friction along the floor, the work non-conservative between moment 3 and moment 4 is not 0. Therefore, we're going to need to realize our equation by calculating the work due to non-conservative forces, in this case friction, and setting it equal to the change in total energy. Change in is always the after moment minus before moment, and so this will be the total energy at moment 4 minus the total energy at moment 3. First, we must express the work due to the non-conservative force of friction. Having observed students perform problems like this for many years, I've seen numerous incomplete solutions when calculating the work due to friction. Let's go step by step. Is that the work due to kinetic friction? No. That's merely the coefficient. Aha! Mu k times the normal force. And the normal force will be the total mass times g. So mu k times the normal force. Is that the work due to friction? No, it isn't. That is simply the force of friction, mu k times the normal force. It's not a work at all. Work is force times distance. Aha! So if they slide across the floor for a distance d, is that the work due to friction? The answer is still no. Work is positive when the force and the displacement are in the same direction. However, in this case, Batman and the Joker slide to the right, but the frictional force is to the left. Therefore, the work due to friction is negative. Mu k times the normal force of mg times the distance d. On the right-hand side, we need to ask ourselves 3 questions at moment 4, and 3 more questions at moment 3. At moment 4, do we have kinetic energy? The answer is no, because they slid to a stop. At moment 4, do we have gravitational potential energy? The answer is no, because we have height equals 0. There are no springs, and so in fact, there is no energy at moment 4. At moment 3, on the other hand, we do have kinetic energy, 1/2 the total mass, times the velocity at moment 3 squared, but no gravity at 3 and no spring. Again, we get a convenient cancellation, in that the total mass on both sides of this equation will cancel out, so that we get the final result for the distance d being equal to velocity 3 squared over twice mu times g. And using the known values for all of these quantities, we get 1.98 meters.